This is fundamental problem 12 from chapter 17. In this problem, the uniform 30-kilogram slender rod is being pulled by the cord that passes over the small smooth peg at A. If the rod has a counterclockwise angular velocity of 6 radians per second at the instant shown, determine the tangential and normal components of reaction at the pin O and the angular acceleration of the rod. So I have three equations that I'm going to use here. I'm going to sum up the forces in the normal direction and the tangential direction. I'm going to sum up the moments about point O also. When I sum up the moments about point O, that's equal to the moment of inertia about O times the angular acceleration. So the first thing I'm going to find is the moment of inertia for the slender rod about point O, which is at one end of the rod. Conveniently, if you look in the back of the book, they give you the moment of inertia about one end of the rod. That's either the x prime axis or the y prime axis. That is 1/3 ml squared, where L is the length of the rod. You could also find this by using the moment of inertia about the center of the rod and using the parallel axis theorem then to get the moment of inertia about one end of the rod. Okay, so the mass of the rod is 30, so this is 1/3 of 30. The length of the rod is 0.9, so times 0.9 squared, and that gives us 8.1. Then I can sum up the moments about point O. That's equal to the moment of inertia times the angular acceleration. I'm looking for the angular acceleration. And I have a force P acting on the rope here. So the magnitude of the force here is 300 newtons. That is at some angle to the rod. And because this is 0.6 and this is 0.8, that is a 3, 4, 5 triangle. Let's do this then. So I have my 300 Newton force here. So this component is 300 times 4/5, and this component is 300 newtons times 3/5. So those are the components for my force there. Then I also have a force of gravity which is acting downward. That's m times g. That is at a distance of 0.45 meters from point O. Since the length of the rod is 0.9, that's half of 0.9. Remember, for the moment, you do R crossed with F, where R is going from point O to the force. So for M times G, you would get rotation in the negative direction. So, or from doing the cross product, you'd have R crossed with F. That gives you something negative. So this is minus, the distance is 0.45, and the force is M times G, so that's 30 times 9.81. And then for the 300 Newton force, when you do the cross product, it's only this component here, the vertical component, which is going to give us something non-zero when we do the cross product, and for R cross F there we get something positive, and this force would cause rotation in the positive direction. So that's plus the distance from pin O to where the force is being applied is 0.6, and then the force is 300 times 4/5 for that component. That's equal to the moment of inertia times the angular acceleration, and this gives me minus 132.44 plus 144 is equal to 8.1 times alpha. Then you can finish solving for alpha, and you should get 1.427 radians per second squared. Okay, so now I can apply Newton's second law in the normal direction and in the tangential direction. Let me copy those equations down first. So the sum of the forces in the normal direction is equal to the mass times the angular acceleration times r sub g. The sum of the forces in the tangential direction is equal to the mass times the angular acceleration times r sub g. So when I summed up the moments about point O, I did not have to include the forces which are acting at point O, but now I am going to have to do that when I sum up the forces. So I'm going to draw a new picture here, and I have this 300 Newton force, and when I break this down into components, 300 times 3/5 gives me 180, and 300 times 4/5 gives me 240. So I have those components which I can put on my free body diagram here. So I have a component going upward, that's 240, a component going to the left, that's 180. I have the force of gravity going downward, that's 30 times 9.81, which is 294.3. And then for the force at point O, well, first let me figure out what the normal direction is and what the tangential direction is. So here's point O, which is fixed, and you have point G here, which is where the mass center is, and the rope is being pulled on here, so the slender rod is going to move this way, and in towards the center, in towards point O, is the normal direction, and the direction that the rod, that point G, is moving in, that is the tangential direction. So now when I break up the force at point O into components, I'm going to say you have a component going in the positive tangential direction, which is upward, and the positive normal direction, which is to the left. Okay, and then if I get something negative for either one of those components, it just means that it's going in the opposite direction. Okay, so now I can sum up the forces in the normal direction. So normal is to the left. I have two forces pointing to the left, so those are both positive. So that's 180 plus the normal component of the force at O is equal to the mass. The mass is 30 times omega squared. Omega is 6. And the distance from pin O to point G is 0.45. And so we can solve that for the normal component, and we get 306. And then we sum up the forces in the tangential direction. Tangential is pointing upwards at this instant. So we have a positive component here, and plus 240, that's pointing upwards, minus the force of gravity because that's pointing downwards, is equal to the mass, which is 30, times my angular acceleration, which is 1.427, times the distance between pin O and point G is 0.45. We solve this for the tangential component, and we get 73.6 newtons. And that concludes fundamental problem 12.